current gain for a common collector one-stage amplifier, single-stage amplifier. So to do this, to assess what AI is, it will be the ratio of the output current, I out, for the whole stage, divided by the current at the input for the whole stage. So the current I out is what feeds the load, and the current I in is what comes in from the source. Now remember, the load also, we would have V out here as well. In other videos, we've looked at AV, which is the relationship between V out and V in. They're approximately the same. In other words, AV, or the voltage gain, was almost 1. Another video we've assessed the input impedance seen from here and here. Now that's going to come in handy when we work with this. So first, it's a matter of what kind of model do you want to use to do the analysis. And what kind of analysis? We're going to do an analysis, and you have a choice between the T model, the pi model, or you could use the hybrid model. So it is up to us. So first, let's go back to the pi model to figure out, for example, the input impedance. Okay? So why? Because I need a model that will eventually yield this. So I'll have a source, and then I'll have RB here, where RB will be equal to R1 in parallel with R2. And all of this would be in parallel with R in this way, at the base. Let's call it R in base. So, and Z total, or R in total, or R in stage in our case, which would be the resistance seen from here, which is this one, R in stage, as seen by the source. What does it see? Okay, from this point down, will be equal to RB in parallel with R in base. Okay, this configuration right here. So how do we find this? Well, we could use the pi model for that. And let's go ahead and do that. So here is the source. Here's RB. Here is beta, RE prime. Okay. Then the current source right here will be pointing up towards the collector, which is here. This here is the base. Okay. And I'm sorry, the collector will be right here. The collector is at ground. Okay. And this here will be beta IB. And we know the current going through here is IB. And we also have RE and RL right here. So what does that mean? That means now, and remember, IN will be this one, right? So if you want to figure out IN out of this, we can do that. So first, let's figure out IB here. And or we could figure out the resistance from this point to this point, which will be RN, based on the fact that IB, right, and VN are related using Ohm's law, right? So Rn base is equal to Vn divided by IB. Okay, but what is Vn? If you look at Vn from base, and remember this is the emitter, so from the base, we're seeing, so this is the base, this point right here, we're seeing beta Re prime, and then this is the emitter, And then we're seeing RE in parallel with RL. And somewhere in there, we're feeding all of this with a current generator to ground here, which this current here, IC, equal beta IB, is important. And then we have an IB here. Now, what do we have? VN is from ground to here, so that's VN. And it's composed of this voltage here, which is IB times beta RE. So we know VN, that's partially equal to beta RE prime times IB. And then what else? Well, we have these two resistors in parallel, and they're being fed by two currents, IC and IB, right? So this voltage here, which is really V out, right? If you think about it, let's write it up here. So V out here is equal to IC plus IB and times RE, this is RE, in parallel with RL. And what is this? That's really beta IB plus IB times RE in parallel with RL. And what is that? That, if you factor IB, that would be beta plus 1 times RE in parallel with RL. So that would be that V out there. So really, what you have for VN is going to be this voltage plus V out, right? So we know this. It's going to be composed of this V out here plus the voltage here. So what is that? That means VN is going to be equal to beta times RE prime times IB plus IB beta plus 1 RE in parallel with RL. Okay, if we're considering everything with a load. Now, can we do some approximation? Beta plus 1, that's approximately beta in the order that beta is much, much greater than 1. So, in other words, Vn is approximately equal to beta times, or let's not forget, this is IB here, and let me factor in beta and IB together. Times RE prime plus RE in parallel with RL. And that gives us, so if we take this up here, that Rn is going to be the Vn we have, beta IB times RE prime plus RE in parallel with RL divided by IB. We can get rid of IB. So Rn at the base is beta RE prime plus RE in parallel with RL. And that's an RL here. Okay, so let me clean up some of the board here because we're going to do some more work. And what we're going to look at now is what is Rn stage. And Rn stage which is equal to RB in parallel with beta RE prime plus RE in parallel with RL. Now, if we did not have a load, it will simply be RE. And now it's a matter of, can we do some approximations if we needed to? So RE in parallel with RL, or simply RE if we didn't have a load. Any of these two together or RE by itself will be much greater than RE prime. So we can say safely that Rn stage is approximately equal to Rb in parallel with beta Re in parallel with RL. Let me just put parentheses here so we know these entities are in parallel with Rb. Okay? That's approximately that. Okay, so we have this model now. Can we figure out In based on that issue? And yeah, I mean, there is, if you think about it, what's going on through here is IB, right? So we can figure out IB versus In here. So let's do that here from the input point of view. And we could easily say that the current IB is going to be equal to In. We're going to use the current divider rule times RB divided by RB in parallel with beta Re in parallel with RL. Okay? Don't simplify the RBs in this manner because this is simply saying is RB in parallel with all of this. Okay, so when you have two resistors in parallel, let's say R1 in parallel with R2, really it's R1 times R2 divided by R1 plus R2. So let's not go trigger happy. We can, because we're factoring here, so you can simplify in one way, but let's leave it alone for now and not mess with it. So can we extract In out of this? Can I extract In based on IB? The answer is yes, I can do that. And so if you look at In, that would be IB times RB in parallel with beta Re in parallel with RL, everything divided by RB. Excellent. Now, how about I out? So remember, I already have this versus IB. Can I figure out what the current I out using IB so I can simplify? The answer is absolutely. What is the current going through here? Think about it. That is IB plus beta IB. In other words, this is almost equal to beta IB, if you want to simplify it that way. Let's do that. So the current going through these two resistors together is IB, which is the current here, that's IB, plus this current IC, which is beta IB, right? We're applying Kirchhoff law here, and that's the current going through these two resistors. So what is I out? Well, we use the current divider rule as well. I out is going to be equal to beta IB times Re divided by Re plus RL. Aha. Now notice here, I have an IB factor and I have an IB factor. Can I do something with it? Absolutely. So now that I'm looking at AI equals to I out divided by In, I can substitute. So I can take this one right here. So beta IB times Re divided by Re plus RL the whole thing divided by IB times RB in parallel with beta RE in parallel with RL, everything divided by RB. And we can say with confidence that AI, we can get rid of IB here, right? A is equal to beta RE times RB, okay? Everything divided by RE plus RL times RB in parallel with beta RE in parallel with RL, and there you have it. And that would be the current gain. Notice it's all purely resistors and the beta factor to figure out what is AI for this circuit.